Hello guys, this is Piyush Raut from Electrical Engineering Department, and this is Digital Signal Processing Lab experiment number 4. In this experiment, we are going to use discrete time Fourier transform to find the pulse period of the given signal. So given these are the formulas for the DFT to calculate for signal x of n. So x of k is given by sigma n equals to 0 to n minus 1 x of n into e to the power minus j 2 pi by n kn. So this e to the power term can be resolved into cos and sines, the complex and the real part using the Euler's identity, and thus the whole formula can be written as xn cos of 2 pi by n kn minus iota sine 2 pi by n kn. So we will be using this formula to calculate the real and imaginary parts of the signal and ultimately to calculate DFT. So let's go into the code. So here x is the array, input array, it is the signal. It is 75, it is sampled at 25 hertz and there are 75 samples. So we are declaring a float pi as constant float, the value of pi. We are creating empty arrays, the xr for the real, storing the real value, xi for storing the imaginary value. And further, as we require this, y is for the moving average filter and the capital X for the uh, absolute value of the signal. So here we are using constant integer n equals to 75, the standard baud rate 9600. So first what we'll do is we'll run a moving average filter over the given signal. Here I'm using the length is equals to 8 for smoothing out the signal, for removing all the high frequency components from the signal. It is a standard moving average filter code, just changing the values and taking the average. Now comes the real code. Here we are using two for loops, nested for loops, to calculate the value of the real and imaginary part for each I and j. So here it is the standard formula. We are multiplying y of j with y of j is the output of the moving average filter. So we are multiplying y of j with the, for the real part we are multiplying it with cos of 2 pi ij by n. So here I is not the like I is the index and j is the nested loop index. So for every I, these values will be the values of some r and some I will be iterated over and over, and they will be summed, and then we are storing it into ith position in the real and imaginary array. Then we need to find the magnitude. So here we are using the capital X array and storing the magnitude of the real and the imaginary part. We are doing basically under root of xr square plus xi square, the real square plus imaginary square, the under root. We are saving it at each position in the capital X array. Now what we have to do is we have to find the maximum frequency component into in the obtained DFT. So we are using standard logic. We are declaring max dash as is equals to 0 initially, and if each of the value for iterating over half of the, we need to find the first peak, so we are iterating over half of the samples. And since the total length was 75, now I am using 36 samples to find the first high frequency, the maximum frequency. So actually the maximum magnitude. So from 0 to 36, I am checking if the value of x of I is greater than max dash. I am changing the value of max dash to the x of I value. So in this way we'll get the maximum value in the first 36 samples. Now I need to find the index of this value also. So what I'm doing is, if the value of x of I is the value of max dash, whatever we found here, then I'm breaking the loop and storing the value into an integer called k. So here we'll find that the maximum magnitude occurs at the ith, here the kth index, and the value is max dash. Now we know that the formula is f is equals to kfs by n. Here n is equals to 75 and the sampling frequency is 25. So I am directly writing it as 3.0, and the value of k we found here, we'll use the same value of k. To calculate the period, what we are doing is we are multiplying frequency with 60. So that way we'll get the period. I am just printing the periods and frequency and plotting all these values. So I have already uploaded the code. Let us see what the serial plotter shows. Here we can see that the green one is the DFT of the input signal, which is given by the blue one. The red one is the moving average filter, and here we can obtain nice DFT graph. We can see that it is symmetric, and the first and the second peaks lie on the either sides. So we are using the value of the first peak. Now let us comment this code and check. Let us check the frequency and the period on the serial monitor. Here we can see that the period is equals to 80 and the frequency is 1.33, whichever whatever we found here, k by 3, and the k value is 4. That is the maximum in the index at which the maximum magnitude occurs is 4. So this approach is using two for loops for finding the discrete time Fourier transform. Since the signal was slow, since the signal was small, the complexity of this function is still n square. For n samples, n is equal to 75. The complexity is 75 square, which is very high and takes a lot of time and computations to calculate the same. So a better option to this is using matrices, and we can use the matrix multiplications to calculate these values easily. So for that we can use octave. uh, I'm using Octave to find the discrete time Fourier transform for the same input of 75 length. So we are here xn is the input, length len is the length of the x of n. Now here I'm creating another matrix, and these are basically the values of 2 pi into linspace. Linspace, what will it will do is it will create all the values from 0 to 1, and the total number of values will be length, that is 75. 75 values between 0 to 1 equally spaced will be created by the linspace function. Then we are creating an we are creating a matrix which has the values of 2 pi times these linspace values. Now n we are defining as 1 to length, basically one from starting from 1 to 75. And here we can say that x of k, the DFT, is basically exp, that is e to the power of minus j w inverse into n multiplied by x and transfers. So here we can say we can run the program and plot the values. Here we can see that we have obtained the DFT for the 75 samples.